In this video, we will explore thread libraries, focusing on the POSIX threads, often called Pthreads, and other threading application programming interfaces or APIs. These libraries are essential for developing concurrent applications that can take full advantage of modern multi-core processors. So, what exactly are thread libraries? Thread libraries are application programming interfaces that provide functions specifically designed for creating and managing threads within a program. They empower developers to implement concurrent programming models, where multiple tasks can run seemingly simultaneously. These libraries serve as an abstraction layer, shielding developers from the intricate hardware-specific details of threading. This abstraction promotes the creation of portable multi-threaded applications, which can run on diverse systems without modification. Now let's explore some common thread libraries. First, we have POSIX Threads or Pthreads, which is a widely adopted standard for Unix-like systems. Then we have Windows Threads, which is Microsoft's implementation for Windows operating systems. Java threads are built directly into the Java language. Finally, the C++ standard library offers its own thread support starting from C++11 and later versions. Let's delve into POSIX Threads, commonly known as Pthreads. Pthreads is a standardized C and C++ threading application programming interface for creating and manipulating threads on Unix-like systems. This includes Linux, Mac operating system, and various Unix variants. Here's a basic example demonstrating how to create a thread using Pthreads. First, include the pthread.h and standard input-output.h header files. Then define a function thread_function, which takes a void pointer as an argument. Inside this function, print thread is running to the console. Finally, return null. In the main function, declare a variable thread_id of type pthread_t. Next, use the pthread_create function to create a new thread. The first argument is a pointer to the thread_id variable. The second argument is null, which indicates that we are using the default thread attributes. The third argument is the thread_function, which is the function that the new thread will execute. The fourth argument is also null, which means we are not passing any arguments to the thread function. After creating the thread, call the pthread_join function to wait for the thread to finish executing. This ensures that the main program does not exit before the thread completes its task. Finally, return 0 to indicate successful execution. Let's explore some of the core functions provided by Pthreads. The first function is pthread_create. This function creates a new thread with specified attributes and starts execution of the thread function. Its syntax is int pthread_create. It takes 4 arguments. The first argument is pthread_t *thread. The second argument is pthread_attribute_t *attribute. The third argument is void open parenthesis *start_routine close parenthesis open parenthesis void close parenthesis. The fourth argument is void *argument. The second function is pthread_join. This function waits for the specified thread to terminate. The calling thread blocks until the target thread completes. The syntax for this function is int pthread_join. Takes 2 arguments. The first argument is pthread_tthread. The second argument is void *retval. The third function is pthread_exit. This function terminates the calling thread and returns a value that can be accessed by another thread using pthread_join. Its syntax is void pthread_exit and it takes 1 argument, which is void *retval. The fourth function is pthread_self. This function returns the thread ID of the calling thread, allowing a thread to identify itself. The syntax is pthread_t pthread_self, open parenthesis void, close parenthesis. Now let's discuss Pthread Synchronization. Here's an example of using a mutex to protect shared data. First, include the pthread.h header file. Then declare a pthread underscore mutex underscore d variable named mutex, and initialize it with pthread underscore mutex underscore initializer. Also, declare an integer variable shared underscore counter, and initialize it to 0. Next, define a function increment underscore counter, which takes a void pointer as an argument. Inside this function, first lock the mutex using pthread underscore mutex underscore lock, passing a pointer to the mutex variable. Then increment the shared underscore counter. This is the critical section where the shared data is being accessed. After incrementing the counter, unlock the mutex using pthread underscore mutex underscore unlock, again passing a pointer to the mutex variable. Finally, return null. This ensures that only one thread can access and modify the shared underscore counter at a time, preventing race conditions. Next, let's examine using condition variables for signaling. Once again, include the pthread.h header file. Declare a pthread underscore mutex underscore variable named mutex and initialize it. Also declare a pthread underscore condition underscore t variable named condition, and initialize it with pthread underscore condition underscore initializer. Additionally, declare an integer variable data underscore ready, and initialize it to 0. Define a function consumer which takes a void pointer as an argument. Inside this function, first lock the mutex using pthread underscore mutex underscore lock. Then use a while loop to check if data underscore ready is false. If it's false, call pthread underscore condition underscore wait, passing a pointer to the condition variable and a pointer to the mutex variable. This will release the mutex and wait for a signal. Once the signal is received, the mutex is automatically reacquired. After the while loop, process the data. Finally, unlock the mutex using pthread underscore mutex underscore unlock and return null. Condition variables allow threads to efficiently wait for a specific condition to be met, avoiding busy waiting and improving performance. Now let's explore thread attributes and advanced features in Pthreads. Thread attributes include stack size configuration, detached state setting, scheduling policy and priority, and processor affinity. Here's a code example: pthread underscore attribute underscore t attribute, pthread underscore attribute underscore init, ampersand attribute pthread underscore attribute underscore set detached state, ampersand attribute pthread underscore create underscore detached. The second advanced feature is thread cancellation, which includes asynchronous termination of threads, cancellation points and states, and cleanup handlers for resource release. Here is a code example: pthread underscore cancel thread underscore id pthread underscore set cancel state, pthread underscore cancel underscore enable null pthread underscore set cancel type, pthread underscore cancel underscore asynchronous null. The third advanced feature is thread-specific data, which includes per-thread private storage, useful for thread-safe libraries and avoids global variable conflicts. Here is a code example: pthread underscore key underscore t key, pthread underscore create, ampersand key destructor underscore function, pthread underscore set specific key pointer. The fourth advanced feature is read-write locks, which includes multiple readers, single writer lock, improves concurrency for read-heavy workloads, and higher performance than mutexes in some cases. Here is a code example: pthread underscore read-write lock underscore t read-write lock equals pthread underscore read-write lock underscore initializer, pthread underscore read-write lock underscore rd lock, ampersand read-write lock / read lock pthread underscore read-write lock underscore wr lock ampersand read-write lock / write lock. Now let's discuss some other threading application programming interfaces. The first is Windows Threads, which is Microsoft's native threading application programming interface for Windows applications. It uses create thread and related functions, critical sections for synchronization, events, semaphores, and mutexes. Here's a code example: handle hthread equals create thread null 0 thread function lp program 0 ampersand thread id. The second application programming interface is C++11 Threads, which is a standard C++ threading library, part of the C++11 standard and later. It is cross-platform standard library solution, standard thread, standard mutex, standard condition variable, future promise for asynchronous results, Here's a code example: include thread standard thread t thread function argument 1 argument 2 t.join. The third application programming interface is Java Threads, which is built-in threading capabilities in the Java language and Java virtual machine. It uses thread class and runnable interface, synchronized keyword and methods, java.util.concurrent package with high-level application programming interfaces. Here's a code example: thread equals new thread, open parenthesis, arrow, open curly brace, system.out.println thread running, close curly brace, close parenthesis, thread.start. The fourth application programming interface is OpenMP, which is an application programming interface for parallel programming in C, C++, and Fortran using compiler directives. It is simple pragma-based parallelism, automatic thread creation and management, work-sharing constructs for loops and sections. Here's a code example: hashtag pragma OpenMP parallel for integer I equals 0, I less than n I plus plus result square brackets I close square brackets equals compute I. Let's compare different threading APIs and discuss best practices. Pthreads is portable to Unix, Linux, and Mac operating systems and has moderate ease of use. Windows Threads is for Windows only and has moderate ease of use. C++11 Threads is cross-platform and has high ease of use. Java Threads is cross-platform and has high ease of use. Here are some threading best practices. Minimize shared data between threads. Use proper synchronization mechanisms. Avoid deadlocks with careful lock ordering. Consider thread pools for task-based workloads. Be aware of thread creation overhead. Design for thread safety from the start. Test thoroughly for race conditions. In conclusion, choose the threading application programming interface that best matches your application requirements, platform constraints, and team expertise. Modern high-level application programming interfaces like C++11 Threads or Java's concurrent utilities often provide better abstractions for common threading patterns. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.